Our last video is brought to you by Bearded Lego Inmate Escapee from Lego Police. I think he's even got a gold tooth and got some crazy eyebrows. So we're just finishing solving logarithmic equations. Here's one last example and then a little bit of a problem we can't solve analytically. So we're going to solve this analytically. Again, recall that our goal was to get a logarithm equal to a logarithm. Now, unfortunately, on the right side, this is not a number. This is now an expression in that natural log. So we're going to have to deal with that when we get there. Now, notice this plus sign means we're going to multiply what we're evaluating log of. I need to figure out what the special name is for that. And we end up with this. And then recall that if you have the same base, and the two logarithms are equal to each other, we just equate the things within the logarithms and then find the solutions to that, and then double check that they're all actually valid solutions. So I'm going to distribute this, and then I'm going to drop the logarithms. So we'll have x squared plus 5x equals 4x minus 6. Again, note we're introducing the potential of extraneous solutions because natural log cannot evaluate values less than 0 or equal to 0. So if any of our solutions are negative or less than 0 or cause something in here to be negative, we're in trouble. Really, if it causes anything up here to be negative. Okay, you all are totally comfortable solving this. I'm positive of that. This is a quadratic. Let's get it equal to 0. And by subtracting 4x and adding 6, oh, I hope that's factorable. It is not. Oh, who made this problem? So we'll have to do the quadratic format. So x equals negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Of course, Desmos would solve this really quickly for us graphically. And let's see, this is negative 1 plus or minus the square root of, oh, look at this. Are these imaginary solutions? Did I mess up somewhere? Let me double check. 4x, we added that over. We subtracted that. Yep. So this becomes 1 minus 24 all over 2. So it feels like we have no real solutions here, right? Because this becomes I square roots of 23. I skipped a step. 1 minus 24 is negative 23, and then to fix that, we get I square roots of 23. So what we're claiming here, then, is because there's no solutions, no real solutions to this quadratic equation, then there's no real solutions to this equation, the logarithmic equation. We'll say no real solutions here. Let's double check. There's a good chance I did something wrong, and that'll be fun to laugh at me if I did. So I'm going to type in the entire equation. We're going to do the intercepts thing, just seeing that it equals 0. I got it. Such a hard word for me to say. So I'm going to subtract that natural log of 4x minus 6 from both sides. And then our goal here is to see where's this thing cross the x-axis, and you can see it doesn't cross anywhere. Oh, good, I was right. There are no real solutions, just as we found. All right, last problem for this section. That is, sometimes we cannot solve things analytically. In other words, using our algebraic manipulations. Maybe when you get to calculus, you'll find some other methods to deal with this. So we can always approximate these solutions using those graphical means that I've been showing. Now, notice here's a clue of why you're not going to be able to work with this analytically, like the problem with the exponentials. Here we have an x within a logarithm, and we have an x as an exponent of some base. Because of that, we're not going to be able to remove x entirely and collect all of the x's on one side and solve. So let's just go right to our graph. Maybe I'll do the intersection because it's easier to say, and that is I'm going to write y equals 2.3 natural log of x plus 10.7. I don't actually like this method because sometimes it's harder to find where the two equations intersect, but I'm going to do it anyways. So I guess I should have, it's probably better to use function notation. So we're going to let the left side be one function. We're going to let the right side be the other function, and our goal is to figure out where do these two things intersect. And those are actually pretty cool graphs, aren't they? Here's your logarithmic graph. That one makes sense. This one probably doesn't. This is that purple? Because that doesn't look like an exponential function, but note we squared it, so that should make some sense because all of our negative values become positive. So it won't be this exponential growth or decay looking thing. It has some weird thing in it. And there's our two solutions, those two x values, negative 3.334 and 2.714. Those are our approximations. So what I will do is to prove how I found this, I will make a quick, oh, wait a minute, I'm missing a solution. Is that a solution there? No, that is not a solution, but this one is. Look at that, there's 3 solutions. Boy, I almost missed that. Okay, so I'm going to draw these 2 graphs and give us some sense of scale. I want to show where it hits the y-axis, where they hit the x-axis. Note the purple graph never hits the x-axis. Oh, I failed on this. Just wait till you see my awful graph. And then here's the other one. So I know it hits at 0, 10, the 1, and then the logarithmic one hits the x-axis at, oh, that's not the one I wanted to give. I wanted to give this one, negative 9.7. And then my 3 solutions that I'm wanting to show, again, don't laugh too hard when you see them. There's this one, negative 9.694. I'm going to hit the home button to zoom back out, negative 3.34. And then the other one is 2.714. So I'll list all my x values and then I'll show you my terrible graph. Negative 9.694, comma, negative 3.3. Is it a 2? No, 3, 4, and positive 2.714. So this is what I very terribly wrote down on my paper. This really, I mean, I was super bad on this graph. Look at that. That peak doesn't match the peak there, so that's a maximum. The 0, 10 is the maximum of this side. Okay, that's it for section 5.5.